All right, so let's see where the conservation of mass for differential control volumes comes from. We're going to derive it in this video. Let's get started by remembering what the conservation of mass says. This is a fundamental law, and what it says is that the rate of increase of mass in the control volume has to be equal to the net rate of flow into the control volume. So in other words, some's coming in, some's coming out, and the delta between those is the rate at which the mass in the control volume is increasing. So for a differential control volume, we're going to use a little cube here, and as always, it's going to have differential dimensions, and so it's going to have a dx on this width and a dz and a dy for its height. And so you can imagine now that if there were flow coming in and out in the x direction, u evaluated at, say, position x here, is happening in this back face, and it's flowing out at this position, a dx downstream, so this is u evaluated at x plus dx. Looking at this thing from the side, same thing happens in the y direction. Flow comes in at a value y, and it comes out at the value y plus dy. So that's the basic setup. Now let's work on this in two different parts. First, let's find the rate of increase of mass in the control volume. So remember that a differential mass can be found by taking the density and multiplying it by a differential volume. Differential volume in this Cartesian thing looks like dx, dy, dz. That's the volume of that little cube. We multiply that by density, and it gives us the differential mass. But that's not what we're after. We're after the rate at which that's increasing. And so to get the rate, we actually need to take the derivative of that with respect to time, d by dt. And so that's all I've done here is take d by dt and subbed in the actual definition of the mass in this little volume, rho times the volume. And this cube isn't changing size, and so all of these things can actually come out of the derivative, and the only thing we're left with is this density, the derivative of the density with respect to time multiplied by the volume. And that is the left-hand side of the conservation of mass. The right-hand side looks like the flow rates. So let's start working on that now, just by looking in the x direction. So in the x direction, we need to find the flow coming in, m dot in, and we need to find the flow coming out, m dot out, in the x direction. And so we can write that as, say, m dot evaluated at position x once again being the left-hand side of our cube. And m dot out, we could call m dot at x plus dx. That's the mass flow leaving the cube at the right-hand side of our cube here, x plus this dx downstream. So mass flows always look like rho v times an a, right? Density times velocity times area. In this case, we want density times the velocity u, which we're evaluating according to our picture at position x on the left-hand side. And we need to multiply by the area that is crossing. We're going to call that ax since it's the area associated with the x direction of the flow. We can come up and look at our little cube here and see that that area is dz by dy, this area of the cube here. And so we can write rho u evaluated at x, that's what's going in on the left-hand side, times the area dy dz. Same idea coming out, m dot out is evaluated at the right-hand side, position x plus dx. We're going to take rho u again, but we're going to evaluate them instead of at x, we'll evaluate at x plus dx. Happens to be at the same area, right? This is a cube, so the left and right-hand side areas are the same. So we have rho u, x plus dx is where we're evaluating it, and then dy dz is the area. Now, when I see something like this, it tells me instantly that I need to do a Taylor series expansion, because that's how we can evaluate rho u at a position downstream dx from the original point x. So let's go take a look at that. Whoa, here we go. Remember, Taylor series expansion says that I can evaluate some function x plus dx, or at a value of x plus dx by taking the value at x and adding to it the derivative with respect to x times dx. Sometimes we write it like this, and so the same notation. All right, so I copied this down here again so we wouldn't be flipping back and forth a lot. M dot at x looks like rho u evaluated at x times dy dz. M dot at x plus dx looks like m dot at x, that's the f of x here, plus the derivative with respect to x times dx, so dm dot dx evaluated at x times dx. That's what this is here. And now we just get to sub in. So m dot at x, well, that's right here, so we put that in. Then we had dm dot dx, so that's derivative of this thing with respect to x, so that's d by dx of rho u. And we need to multiply it by a dx. And then all of that is getting multiplied by the area, the dA here, which conveniently I left off of this row. There should be a dA there. You know what, let's fix that real quick. This. Oh, no, it shouldn't. Never mind, I made a mistake because this is m dot, not rho u. M dot is rho u times the area. So that's what this is on the right. This is the area. All right, now we want the net flow rate in. That's what the right-hand side of our law says we want. So let's look at that real quick. That would be the difference between what came in minus what came out. Well, what comes in is this rho u evaluated at x times dy dx. That's the first thing we came up with. And what goes out is the thing we just came up with, m dot at dx, or x plus dx, because that's what we wrote. So we have all of this business that we just came up with here. And what's nice is you can see this term, rho u dy dz, cancels with this term, rho u, and we're left only with the negative d by dx of rho u x. And conveniently now you have a dx, you have a dy, and a dz that all showed up. Now, we could go through that exact same exercise, and I invite you to do so if this was confusing to you, to get the flow rate in the y direction using rho v, and the flow rate in the z direction using rho w. And this is just going through each of the four sides of our cube. Now we're going to sub all of that into the law. Okay, so the left-hand side, remember, was d rho dt with this stuff, and then the right-hand side was the flow rate in each direction. And what's neat is they all have the same differential dimensions multiplied on them, and so they cancel out, and we're left with a fairly elegant equation here, which is the derivative of density with respect to time plus d rho u dx, d rho v dy, d rho w dz. This is called the continuity equation, which is just a fancy word for conservation of mass for a differential volume.